This video covers section 4.10 out of the OpenStax Calculus book, Volume 1, entitled Antiderivatives. Let's take a look at what we're trying to learn in this particular section. What we're discussing now are what are known as antiderivatives. You can think of an antiderivative as an undue function for the derivative. So in words, you would simply mean that this undoes the derivative. Now, this is the operation that is the inverse of the derivative operation. If the derivative goes in one direction, then the antiderivative goes in the opposite direction. Why would we possibly need to be able to find an antiderivative or to undo a derivative? One of the classic examples of where you need to be able to undo derivatives is when you think about motion along a straight line, otherwise known as rectilinear motion. Remember that we have a relationship between the distance function, the acceleration, and the velocity function, where basically the position, if you take the derivative, you will get the velocity, and if you take the derivative of velocity, you get acceleration. Now suppose that you know what the acceleration function is, but you don't know what the velocity is or what the position function is. If you know the acceleration function, you can undo the derivative to get to the velocity function. And then you can undo the derivative on the velocity function to come up with a formula for the position function. In general, we say that a function represented by an uppercase letter f is an antiderivative of the function lowercase letter f if capital F prime of x is equal to lowercase letter f of x for all the x in the domain of the function lowercase f. In other words, if capital F is the antiderivative, the undo the derivative on f, then if you redo the derivative on capital F, you should get back to the lowercase function, lowercase f. Now let's move on. From the second corollary to the mean value theorem, we know that two functions f and g, where their functions have equal derivatives, have to either be the same function or only be different by a constant. The reason is when you take the derivative of any constant is 0, and so it disappears. In this case, we can use this to come up with a theorem about the general form of an antiderivative. Let's suppose we have a function that we will name lowercase f, and its domain is on the interval capital letter I. We'll let uppercase letter f be an antiderivative for lowercase function f over that interval, capital I. Then for every constant, and constant here does mean any real number, for each constant c, the function given by uppercase letter capital F plus c is also an antiderivative of lowercase letter f over the same interval I. The reason is if you take the derivative of any capital letter f of x plus c, the derivative of the c will go to 0, and the derivative of capital letter F will give you lowercase letter f. Thus, we know that, in fact, when we find antiderivatives, we're finding what's called a family of functions. The family of functions that we're finding is given by this f of x plus c. This is a family of functions representing all the possible antiderivatives of the lowercase function f. Here's another part of this general theorem. If capital letter G is an antiderivative of lowercase f over the interval I, there must be some constant c, which represents the difference between the capital letter antiderivative function g and the capital letter antiderivative function f. In other words, they have to be essentially the same graph, but with one shifted above or below the others. The most general form, then, is simply to write capital F of X plus C. Let's take a look at what this means geometrically. On a graph, what this means is that we have a family of functions which represents any of the antiderivatives in that entire family of antiderivative functions. G, which is the one in black here, is one of these antiderivatives. And if we add or subtract various constants, we'll get other antiderivatives. Notice they all have exactly the same shape. They've just been vertically translated up or down. You'll see the same thing here on the graph to the right. These are the antiderivative functions of 2x, where the original function, lowercase f, was 2x, and the basic antiderivative function is y equals x squared, or uppercase f equals x squared, which you see here. Notice if you took the derivative of any of this class of functions in this family of functions, you will get lowercase letter function 2x. Just as we have notation for the derivative, we need to have notation for this antiderivative function as well. The notation for the derivative is usually the prime notation or the d by dx notation that Gottfried Leibniz invented in the late 1690s, or early 1690s rather. Both of these mean take the derivative of the function named f. We need some kind of notation to represent the antiderivative or the undo the derivative function. For historical reasons, we use what's called an integral symbol. The integral symbol looks like an elongated S, and you'll see it right here in the center of the screen. This elongated S extends both above the line and below the line if you're writing it on lined notebook paper. You'll notice that the bottom of the function where the f of x is would sit directly on the line, but the upper part of the integral symbol extends above it into the line above. In fact, this integral symbol is an elongated S. For reasons that will become clear in Chapter 5, the S here stands for the word sum. It also is a representation of the Greek letter sigma, which is written with points on the ends. They took the Greek letter sigma, which represents sum, and they stretched it and rounded off these sharp corners and created the integral symbol. Every time you see that integral symbol, it is followed by a function called the integrand. In the example that you see here in the center, the integrand is represented by f of x. F of x is the function or the expression on the inside of the integral. So let me give you an example. I could write that the integrand is x squared plus 1, the quantity. That would represent the integrand. However, there is a third part to any antiderivative notation. When written in this form, there must be present all three parts. You must have the integral symbol at the beginning on the left, you must have the integrand in the middle, and as a bookend to the integral symbol on the far right, you must have the differential. This is the same differential that we looked at in Chapter 4 earlier. This dx does also represent delta x. It also tells us what the independent variable is and what we're going to be undoing the derivative with respect to. When you're in single variable calculus, as we are in Calculus 1 and 2, this doesn't seem to make a lot of sense to students, and they have a bad habit of leaving off the dx. To discourage that behavior, you can be sure that on a test, if you leave off the dx, you will automatically lose 20% of the points immediately. The dx is important because when you get to Calculus 3 and beyond, we do in fact live in a three-dimensional world, and we use time to represent the fourth dimension. That means in the future, your function, your integrand, may involve multiple variables, x, y, z, and possibly time as well. If you do not have the differential, you will not know which variable to undo the derivative with respect to. I will be pretty hard-nosed about this, so make sure that you include that dx. For similar reasons, when you are done undoing the derivative and you have your antiderivative function, you need to remember that it is only accurate up to that constant plus c. I will also take off 30% of the points if you don't include the plus c, which means on any integration, if you leave off the plus c and the dx, you're starting with a 50% for that problem. Be sure that you include the plus c on any indefinite integral and that you always include the differential on all integrals. Integrals must have three parts: the symbol, the integrand in the center, and the differential. This notation represents all possible antiderivatives of f. What this is going to give us, if we now want to write this down, is it's going to give us some capital F of x up to that constant that I said was worth 30% of the points. F of x plus c, where the f now is not the original integrand function lowercase f, but is instead uppercase f, representing the antiderivative function for that particular function, lowercase f. You'll find in the blue box now in the center of the screen the formal definition. For a given function, lowercase letter f, the indefinite integral of lowercase letter f is denoted with the integral symbol, the function lowercase letter f of x as the integrand, followed by the differential dx. This is the most general antiderivative of that lowercase letter f function. If you let capital letter f or uppercase letter f be any of the antiderivative functions of lowercase letter f, then you can write that that integral is equal to uppercase letter f plus some constant. The expression with lowercase letter f is called the integrand, the thing being integrated, and the variable x is the variable of integration. The dx is the differential, just as it was for derivatives. I know that you've finally gotten down all the rules for derivatives of functions, but unfortunately, you now have to learn how to undo all of those rules. In other words, now that you've got it down and you're not making mistakes anymore, I'm going to ask you to go backwards. This is going to be somewhat difficult at first, and it's not uncommon for students to get messed up and to do the wrong operation at the wrong time. Give it some time, it will get better, and you will eventually come to understand on a deeper level what it means to take the derivative and what it means to take the integral. It can take some time, however, so be patient with yourself and don't be surprised if you sometimes take the derivative when you're supposed to integrate, and you sometimes integrate when you're supposed to take the derivative. Now, when I say integrate, I am talking about the operation of evaluating the integral. Integration is another way of talking about and finding the antiderivative. Antidifferentiation and integration mean essentially the same thing for indefinite integrals. One of the first rules we learned when we did derivatives was the power rule. Now we have to undo it. To undo it, though, it would be helpful if we could first talk about what the rule for derivatives was. So I'm going to write that below. To be able to do integration, we need to be able to undo the power rule. For the derivatives, when we apply the power rule, we pull the power on the variable x that corresponds with the differential dx, and we pull it to the front. It becomes a factor that is multiplied by the original base to the power reduced by 1. To undo that, we have to reverse the order of operations. So let's go back through the power rule for derivatives and talk about what we did and in what order we did it. First, we took the power in and pulled it to the front. Then we subtracted 1 from the power. So to undo this, the first thing we need to do when we integrate or antidifferentiate x to the n is to add the 1 back onto the power that we took off last. In other words, these operations are done in reverse order. In the power rule for derivatives, the last thing I do is subtract 1 from the power. So in the integral or the antiderivative, the first thing I do is add 1 back to the power. So the power becomes n plus 1. What did I do right before that on the power rule for derivatives? Before I subtracted 1 from the power, I pulled the power that was originally on the variable to the front. By multiplying by it, I now need to be able to undo that through division. So what I will do is I will divide by the new power, which was the original power. In this way, we can come up with what's known as the power rule for integrals. The integral of x to the n is x to the n plus 1 divided by n plus 1 plus some unknown constant. The constant represents those infinitely many family of antiderivative functions. Note that this does require that n not be equal to -1. If n is -1, we would end up with 0 in the denominator, and we know that can't happen. What function is it that would give you that -1? If we're to rewrite the integral, let's take a look at that integral very quickly. That integral would look like the integral of 1 over x dx. What function did we know that had a derivative of the form 1 over x? If you think about it, you'll remember that the function whose derivative gave you 1 over something was natural log. In this case, we will get the natural log of x plus the constant. However, there is something we need to add. The thing we need to add here are absolute values around the x. The absolute values are required on that because if we remember what our natural log function looks like, we know that it is not defined when x is 0, nor is it defined on the negative half of the coordinate plane. That means that x must be strictly positive to make this defined. Note that x equal to 0 is already eliminated from the domain because the integrand would not be defined there. The absolute values then only eliminate the part that's still possibly in the running, and that's the negatives. Technically, we are not going to be looking at this particular antiderivative until much later in Chapter 5, but just in case it crops up somewhere, I thought I'd go ahead and give it to you here. Technically, I believe it's either in section, 5.6 or 5.7 in Chapter 5. But I've given it to you here in case you run across it in one or more examples. Now we need to think about all the different formulas that we've come up with. On the left, you'll see the derivative formula, and on the right, you'll see the indefinite integral, or the antiderivative that corresponds to it. Remember that the antiderivative is another word for indefinite integral. Antiderivative and integration are similar processes, the same process, in fact. The derivative of a constant is 0, so how can I integrate a constant? If I'm going to integrate a constant, it must mean that I took the derivative of something and got the constant. which means originally I had to have had an x there, which means that my antiderivative has to be kx plus c. You'll note on this second line here that this is in fact the power rule for both derivatives and integration. In the next line down, you will see that I have written the one that I developed for you up above. In the next line, you'll notice we have the derivative of the exponential, which is the exponential. This makes e to the x our most favorite function for both derivatives and integration, because whether you take the derivative or the indefinite integral, you still get e to the x. When you do the antiderivative, however, don't forget that you are required to put the plus c, since any value of c would work. E to the x plus 2, e to the x minus 10, e to the x plus pi, all have the derivative e to the x. Then we have our trig functions. Remember that we have sine, cosine, and tangent. These are the three that most students begin with when they learn trig. The derivative of sine is cosine, which means the antiderivative of cosine is sine. In other words, what do I take the derivative of to get cosine? Sine. What do I take the derivative of to get sine? Well, the derivative of cosine is negative sine, so to get positive sine, I should have taken the derivative of a negative cosine. Thus, the antiderivative of sine of x, or the indefinite integral sine of x dx, is negative x plus a constant. Since the derivative of tangent is secant squared, the integral of secant squared is tangent of x plus c. In the next box, you will see the remaining three trig derivatives for cosecant of x, secant of x, and cotangent of x. Since the derivative of cosecant is negative cosecant cotangent, integrating cosecant cotangent gives us the opposite of cosecant. You could also put a negative in front of the integral, which would negate this negative here and give you back cosecant. Since the derivative of secant is secant tangent, the integral of secant tangent is secant of x plus the constant. Then towards the bottom, you will see that I have put down the primary three inverse trig functions. We did not list the second three, which are all the inverse co-trig functions: inverse cosine, inverse cotangent, and inverse cosecant. The reason is these three are the primary three that are used and the ones that form the core of a technique that we use in Calculus 2, which is called trig substitution. These three are the most important. Which of these formulas do you think I expect you to have memorized for the exams? That's correct. Everything except the bottom three. The ones above it are definitely ones you need to memorize. There are U forms for these, and you will see the U forms on the handout in the Learning Management System. Let's move on to the next part. In general, you need to remember that the product of antiderivatives will not be the antiderivative of a product. That's just a consequence of the product rule. Remember that the derivative of a product, f times g, is f prime g plus g prime f. In other words, the derivative of a product is not the product of derivatives, so it is not true for antiderivatives either. In general, any integral that involves a product, a quotient, or a composition of functions is much more complicated. In fact, we spend fully 1/4 to 1/3 of the entire semester in Calculus 2 learning how to deal with most products and quotients in the Integrand. We will learn a technique this semester to deal with composition, which is called U substitution. However, we will not be ready to look at that until section 5.5 near the end of the course. The only thing that you're allowed to do simply with an integral are the only things you're allowed to do simply with a derivative. The derivative of a sum is the sum of the derivatives. So the integral of a sum is the sum of the integrals, and also the same for a difference. You can also multiply by a constant and pull the constant out of the integral, just as you can pull it out of a derivative. So the constant times the integral f of x, you could pull the k to the outside of the integral and not change it. Likewise, you could split this integrand up into the integral of f of x dx plus or minus the integral of g of x dx. Each time you write the integral symbol, you must be sure to include a dx for that specific symbol. Let's take a look at some examples now. In the first section of examples, we are going to show that uppercase letter f of x is an antiderivative of lowercase letter f of x. To show that that is true, that means that we need to show that the derivative of uppercase letter x with respect to x is equal to the function f of x. Let's take the derivative of capital F of x now and see if we can in fact get lowercase letter f. The derivative of 5x cubed would lead to 15x squared by applying the power rule. The derivative of 2x squared would lead to 4x, and the derivative of plus 3 would give me plus 3. This shows that since this is equal to the original lowercase letter f, this does prove that capital letter f is an antiderivative function of lowercase letter f of x. However, there are many possible antiderivative functions for this. In fact, I could take any function that looks like f of x, but change the constant, and I will get exactly the same derivative, which means all of those functions are also antiderivatives of lowercase f of x. Now let's look at the next example, which is problem 467 out of your textbook. Looking at this problem, I want to show that uppercase letter f of x is an antiderivative for lowercase letter f of x. Again, I need to show that the derivative of f of x uppercase is equal to f of x lowercase. I need to show that d by dx of uppercase f equals f of x, or using the prime notation, capital F prime of x equals lowercase f of x. In that case, what I want to do is compute the derivative of the first function. Since this is a product, I will need the product rule. If I think of this first one as the first factor and e to the x as the second factor, then I can take the derivative of the x squared to get 2x and leave the second factor alone, plus the derivative of the e to the x factor is still e to the x times the first factor, x squared. Now to get it to look like the lowercase letter f function, I need to factor out the common factor e to the x. This leads to e to the x is equal to, and writing what's left in descending order, I get x squared plus 2x. This does show that since the derivative of the antiderivative function was the original function, that uppercase letter f is an antiderivative of lowercase letter f. Let's look at the next example. In the next example, which is problem number 468 out of the textbook, we have that the antiderivative function is cosine of x, and the original function, the integrand, is negative sine of x. In other words, what they're asking us to show is that the derivative of cosine of x has to be equal to the antiderivative of negative sine of x dx. In order to prove that, I take the derivative of both sides. If I were to take the derivative of the left side, the derivative of cosine of x would give me minus sine x, just as I did in the ones above. On the right side, the derivative applied to an integral where the differential matches the differential of the derivative basically means that I'm a dog chasing my tail. I've gone in a complete circle. I undid the derivative with the integral notation, and then I did the derivative again, which means I went nowhere, and I end up with negative sine x. This proves that that is an antiderivative function for negative sine x. Let's move on to the next section of problems. In the next section of problems, we want to find the antiderivative function, uppercase letter f, for each possible integrand function, lowercase letter f. In this case, we are not given the candidate that we think will be the antiderivative function. Instead, we are to find it. To find it means that we will need to apply a process similar to what we did in the last problem. In the last problem, remember that I simply said the derivative of this would be the derivative of its other representation, which is the integral. In other words, I will need to integrate or find the antiderivative of this lowercase function here. So to do that, I will simply write that uppercase f of x needs to be the undo the derivative of the integrand 1 over x squared plus x with respect to x. You'll notice that I have put parentheses around the integrand. This is standard when the integrand consists of more than one term. They should technically be there, though I typically don't take off if you don't. There are professors that do, so you want to get in the habit of putting parentheses around the integrand. The parentheses should follow the integral and precede the differential dx. It's also a good way of making sure that you have your bookends, since the integral symbol should be outside on the left and the differential should be outside on the right. Now let's look at this and see if we can undo the derivative. It is difficult to know what the antiderivative of 1 over x squared is in its current form. So I will apply some algebra to rewrite it instead as x to the negative 2 power. This will let me think of it using the power rule. Remember that for a derivative, you pull the power to the front and then subtract 1. Working backwards, we need to add 1 to the power and then divide by that new power to compensate for having multiplied by it. That means that in this problem, I need to take and add 1 to the power and then divide by this new power of negative 2 plus 1. On the second term, I'm going to do the same thing, except on the second term, my power was not originally written. It's still there, though. It is a 1. I still need to add 1 to the power and divide by that new power, 1 plus 1. Because I'm finding an antiderivative family of functions, don't forget that it is required that you put plus c. This is worth a lot of points. It is a major concept in calculus, and I will be a stickler to make sure you put it on there. Rewriting this by simplifying the powers then leads us to the next line. The next line would be x to the negative 1 divided by negative 1 plus x squared over 2 plus a constant. Could I simplify that further or rewrite it in a better form? The answer is yes, you probably could. For one thing, you could pull the negative 1 on the power would drop the x to the denominator. That means I could rewrite it as negative 1 over x plus x squared over 2, or 1/2 x squared, plus c. This would be the antiderivative function for the original. If I were to take the derivative of this function, I should be able to get back to the original function 1 over x squared plus x. Just for fun, let's check it on this problem to make sure it does take us backwards to where we started. Let's take the derivative of this and see if we get back lowercase letter f. So the derivative with respect to x of negative 1 over x plus x squared over 2 plus c. I'm going to first rewrite the first term here as negative x to the negative 1. That will make my derivative process simpler. Then I'm going to rewrite the second term as 1/2 times x squared. Now when I apply the derivative, the power rule will bring the negative to the front, and a double negative will give me a positive x, and then I will subtract 1 from the negative 1 power to get negative 2. On the second term, the 2 power pulls to the front to multiply by the 1/2, and then I reduce the power on the 2 by 1 to get 1. The derivative of any constant is 0. You can write plus 0, or you could leave it off. It's not going to make any difference. If I rewrite this, this gives me 1 over x squared. The 2's will cancel, and I get plus x. Was that our original function? If we scroll up, was lowercase letter f of x 1 over x squared plus x? Indeed it was, so I've verified that I definitely have the right answer. Let's look at the next problem. The next problem is 471 out of the textbook. This problem mixes up the different types of functions. We have an exponential e to the x. We have a polynomial type term, negative 3x squared, and we have a trig term, sine of x. In order to find the antiderivative function, we will need to split it into 3 separate integrals. I will then be able to write the following. The antiderivative function, which is the indefinite integral of e to the x minus 3x squared plus sine of x, close the integrand times the differential dx. Now I can rewrite it since those are added and subtracted together. I can rewrite this by splitting up the integral. And by that I mean that I will write the integral of e to the x dx minus the integral of 3x squared dx. You have a choice whether to put the minus between the integrals or to write this as a plus and the 3 as a negative 3. Typically, we would leave the negative in between as a subtraction. And then plus the integral of sine of x dx. Notice that each time I write the integral symbol, it must have its own differential as a bookend at the end. Remember, if you put up books on a shelf and you don't have a bookend on each end, they'll all come falling off the shelf and crash on top of your head. All right. What is the antiderivative to e to the x? Well, the antiderivative of e to the x is the same as the derivative of e to the x, which is just e to the x. Technically, this would give me also a plus constant. I put C1 to represent it's the constant from the first integral. What about the second integral? The minus will stay in between, and I have 3x squared. To apply the power rule for integrands, I need to add 1 to the power, so the 2 becomes 2 plus 1, or 3, and I need to divide by the new power, which is 3. I also will get another constant on this one, which I can call C2. Technically, all of this would be in parentheses with the minus on the outside. You'll notice in a second it's not going to make a lot of difference. For the third integral, I need to know what trig function I took the derivative of to get positive sine. To undo the derivative, I know the derivative of cosine would give me negative sine, So it must be that I had negative cosine, because the derivative of that would give me positive sine. It also carries its own constant, C3. The next step is one that we use all the time in various levels of calculus and differential equations. What we're doing in the next step is we're rewriting all the non-constant terms at the front, the e to the x minus x cubed, since of course our 3's canceled, minus cosine of x. At the back, I'm simply going to write plus c. Now you may say, well, what happened to c1, negative c2, and c3? Well, if you have c1 minus c2 plus c3, isn't that still just a constant? Since a constant minus a constant plus a constant is a constant, we can roll them all together and ball them up and call it all plus c. This is very typical to do, and we do it a lot in both calculus and differential equations. Let's take a look at the next example, which is mostly a mixture of a polynomial, 3x minus x squared, and an exponential e to the x. On this problem, I am going to write that the antiderivative function would be the indefinite integral of the integrand e to the x plus 3x minus x squared, close the integrand with the differential dx. In order to evaluate this, I will split it into 3 separate integrals. This will give me that the antiderivative function is the integral of e to the x dx plus the integral of 3x dx minus the integral of x squared dx. Remember that one of our rules said that if I have a constant, I could pull the constant outside. So it is fine to write the 3 on the other side of the integral. The only thing that can't go outside the integral is anything that has the same variable as is found in the differential. The differential tells you which variable the integral is with respect to, which is also the only thing that can pass neither in nor out of the integral. To evaluate this antiderivative, I will apply it on each separate integral. The antiderivative of e to the x is e to the x. I'll wait to put the plus c until I'm done with all of the integrals, then I'll ball them all together into 1 plus c. The antiderivative for 3x, since the power on x is 1, is to add 1 to the power on x, so I would come up with 3x to the 2 and divide by the new power, which is 2. Applying the same rule on the integrand x squared, the power was 2, so I add 1 to it to get 3 and divide by the new power, which was 3. Don't forget that since you are evaluating an antiderivative, that you need to slap a plus c on the end. This will give us the antiderivative function for the original function given up here as lowercase letter f of x. Now let's look at this function, which is problem number 476 out of your textbook. This one is a radical. You know that the derivative of a radical gives you 1 over 2 the radical, which should make you suspicious that the antiderivative function will have something to do with the square root of x, possibly with a constant. Let's look at it and see what we get. On this problem, I'll write that the antiderivative function, uppercase letter f of x, can be given by the indefinite integral of the integrand 1 over the square root of x with respect to x. The differential is the with respect to x part. The next step is to rewrite the integrand in a power form so that I can apply the power rule for integrands. This would give me x to the negative 1/2 power. The negative lifts it out of the denominator to the numerator, and the square root is the 1/2 power. Now I can apply the power rule for integrands to get x to the negative 1/2 plus 1 divided by -1/2 plus 1. In order to add, you do need to have a common denominator, so many students, instead of writing plus 1, will instead go ahead and write plus 2 over 2, since 2 over 2 is the unit fraction which represents 1. This would tell me then that my antiderivative function up to that constant plus c must be x to the 1/2 power divided by a 1/2. Remember that when you're looking at the denominator of the denominator, by changing from dividing by a fraction to multiplying by the reciprocal, the bottom of the bottom becomes the top, and this will give me 2, and then I can rewrite the 1/2 power as the square root of x, and don't forget your plus c. That means that the antiderivative function is in fact a multiple of a square root. It is 2 the square root plus the constant. Now let's apply it to another function where the integrand is written with rational exponents. For this problem, we're going to have the antiderivative function, uppercase letter f, as the indefinite integral of the integrand x to the 1/3 power plus, in parentheses, 2x to the 1/3 power with a dx on the end. Now, in order to do this, we will have to be cheating a little bit and going beyond where you really are at this point in the course. This requires us to actually do a bit of U substitution, but before we've learned it. I have tried very hard to take all those problems out of the homework, and hopefully I managed it. Remember that the 1/3 power does represent the cube root. If I'm going to split these into two separate integrals because they're added, that means that each one gets its own integral symbol and its own differential dx. The second one, notice that the integrand has an inside function of 2x. The first one, we can simply apply the power rule already. The power rule applied to that one would increase our power by 1 and enable us to write x to the 1/3 plus 3/3, which would give us 4/3. So we would be dividing by the new power of 4/3. The problem here is that the base isn't simply x, but instead is 2x. If I'm going to undo this, I need to compensate for the fact that I have a 2 on the inside. To compensate for it, I would typically need a 2 to go with the derivative on the outside, or the differential. This is a more difficult topic and one that we're not really going to get into very much until we get into U substitution in section 5.5. But I did want you to see here at least how you would start to go about to figure this out. We know that we need to lift the power on this to be from 1/3 to 1/3 plus 3/3, or 4/3. The problem comes when we try to undo things. If we are to take the derivative of this, we should get back to the original integrand function. Don't forget to add your plus c. Hold on for now to this second middle part here, now with a dashed red circle around it, because it is not complete. This will not give us back the original integrand. We need to see what's missing to know how to fix it. And the reason it is missing is because the base is not x, but 2x. The 2 is going to affect the antiderivative function. To simplify the first one, however, the bottom of the bottom goes to the top, and we end up, instead of dividing by 4/3, we can multiply by 3/4, which gives us 3/4 x to the 4/3. The second term would also multiply by 3/4. The base is 2x raised to the 4/3 power plus a constant. The question is, if I were to take the integral, would I get back the original integrand? This function here is our antiderivative function candidate, but we're not sure that it works. We know that when we take the derivative, it should give us back this integrand function. Let's take the derivative of this antiderivative and see what we get. We'll do this in a blue color so that we can distinguish it. The derivative of f prime of x would pull the 4/3 using the power rule for derivatives to the front, which would give me 4/3 times 3/4 x to the subtract 1 from 4/3 means subtract 3/3. For the second term, I would also apply the power rule, but because the inside is 2x, a composed function, I'll also need the chain rule. The chain rule presence is what is going to mess up our antiderivative function. This gives me the 4/3 power from here coming to the front to multiply by the 3/4, leave the base function alone, subtract 1 from the power, and then multiply by the derivative of the inside. The derivative of 2x is 2. It's this 2 that's going to mess things up. The derivative of the constant, of course, is just 0. Notice that for my antiderivative function, the 4/3 times 3/4 cancels, and I do get x to the 1/3 power, which does match the first term of the integrand function. However, on the second part, notice that I have the 4/3 and 3/4 canceling, the 2x to the 1/3 power, but I also have at the front a constant of 2. This constant of 2 is not present in the original integrand. In order to get the constant of 2 off of here, I will need to have divided by 2, which means that this will have to be divided by 2, which means that up here I should have had, up in the original, up here, a times 1/2, which means this must also have a 1/2. Because I have a times 2 for the chain rule of derivatives, to compensate for the antiderivative, I have a divided by 2, and that will give us the 1/2 coefficient that we need to make the derivative of the antiderivative come out to equal f of x. Now let's take a look at the next example, 481. 481 is primarily a trig function. Again, let's go ahead and apply the antiderivative operation to the integrand secant squared of x plus 1 with respect to x. I can split this into two integrals, secant squared of x dx plus the integral of 1 dx. In fact, you don't need to write the 1. The integral of dx implies that there is a 1 in between. What function do you know whose derivative is secant squared? That's right, it's tangent. This would give me the tangent of x. How about undoing this one? What function do you know that when you take the derivative, you just get 1? That's right, it's got to be x. And then don't forget the constant which goes on the back. One of the last examples in this section is simply the integral f of x equal to 0. To do this one, again, we'll simply apply the antiderivative operation to 0 dx. However, 0 times anything is still 0, which means that our antiderivative function here is 0 plus the unknown constant. Since 0 plus a constant is a constant, that means that the antiderivative function is any real constant number. Now let's take a look at the next and final example in this section, 1/2 cosecant squared of x plus 1 over x squared. Let's find the antiderivative function for this integrand. We'll find the indefinite integral of the integrand, and we will split apart the two different terms into two separate integrals. I will also this time pull the 1/2, which is a constant on the first term, outside the integral. I get the integral of cosecant squared of x dx times the 1/2 plus the integral of 1 over x squared dx, which can be rewritten as x to the negative 2 dx. Remember that the derivative of cotangent will give us negative cosecant squared, so the derivative of negative cotangent would give us cosecant squared. Therefore, the antiderivative of cosecant squared would be a negative cotangent of x. What about the second integral? To do the second integral, we need to apply the power rule for integrands, which means add 1 to the power so that negative 2 plus 1 becomes negative 1, and then divide by the new power. Don't forget to add the plus c. When we do that, remember that the negative 1 in the denominator can be written in the numerator, so that I can get negative 1/2 the cotangent of x minus 1 over x plus a constant. The next two examples are simply the same as what we've been doing. They're simply already written in their integral form. Let's go ahead and handle those now. To handle this particular integral, the first thing that I would do is rewrite the integrand in terms of power functions. That is, the variable x raised to a power. In this case, I can rewrite the square root of x as x to the 1/2, so that the first term becomes 4 times x to the 1/2. The second term, the fourth root of x, can be rewritten as x raised to the 1 divided by 4 power, all with respect to the variable x. Now I can split these into two separate integrals, and I can pull the constant coefficient of 4 to the outside of the integral. This gives me x to the 1/2 with respect to x, plus the integral of x to the 1/4 with respect to x. Applying the power rule for integrands leads to 4x 1/2 plus 2/2, which will give me 3/2. And I can divide by 3/2, or I can think of dividing by 3/2 as multiplying by the reciprocal 2/3. In fact, you need to get good at thinking of dividing by the fraction as multiplication of the reciprocal, so that when I recognize the new power as 5 over 4, I know that I will multiply by the reciprocal 4 over 5. And don't forget plus c. Cleaning up the algebra a little bit will lead to the next term. We will end up with 4 times 2/3, the reciprocal of 3/2, x to the 3/2, plus 4/5, x to the 5 over 4 plus c. By combining the 4 and the 2/3, I finally get, for my final answer, 8/3 x to the 3/2 power plus 4/5 x to the 5/4 power plus a constant. That is the antiderivative function, whose derivative will give me back the original integrand. Let's look at the next one. The next one can actually be done a little bit simpler if you recognize that there is a trick that can be applied. You'll notice first off that there is a fraction, which means there's division. But if you're remembering, I said that we wait until calculus 2 mostly to deal with any division or products in the integrand, which must mean that there is some way to get around the division, and there is. The denominator of this fraction is a single term, a monomial expression of x cubed. Whenever that occurs, you should rewrite the original integrand by separating each factor from, or each term from the numerator divided by the single factor in the denominator. This would give you 14x cubed over x cubed, 2x over x cubed, plus 1 over x cubed as the new form of the integrand. Then you can simply proceed as before, but split each of those terms into its own separate integral. You can go ahead and do the cancellation if you have any. X cubed divided by x cubed leaves behind only a 14 with respect to x. The function whose derivative is 14 is 14x. On the second term, I can cancel the monomial x from the numerator, which will give me x squared in the denominator. I will want to rewrite this one as 2 from the numerator being pulled outside times the integral x to the negative 2 power dx. Note that the x squared that was in the denominator is now written in the numerator by changing the power to the opposite sign. The third term, 1 over x cubed, cannot be simplified algebraically, but I can lift the integrand from the denominator into the numerator by changing the sign of the exponent from 3 to negative 3. Now I will apply the power rule for integrals on the second and third integral. The plus 2 from the outside continues as a constant at the front. Now what I will have on the next part is adding 1 to the power, which was negative 2, and it becomes negative 2 plus 1, which is negative 1. So I have the 2, x to the negative 1 divided by the new power of negative 1. For the last integral, I'm going to apply the power rule for integrands, which is going to raise the power by 1 from negative 3 to negative 2 and divide by the new power of negative 2. Don't forget plus c. When I simplify this, I get 14x minus 2 divided by x when I drop the x to the negative 1 to the denominator, minus 1 over 2x squared. Notice that the x to the negative 2 dropped to the denominator, but the 2 that was in the denominator stayed put. The negative I pulled between to serve as the minus sign, and then I have plus c. This becomes the antiderivative function for the original integrand, or the value of the indefinite integral. In the next part, we wanted to briefly talk about what a differential equation is and what an initial value problem is. We won't do a lot of these here. We're simply going to do 1 or 2. In this case, let's see what it says. A differential equation is an equation that relates an unknown function and one or more of its derivatives. The function dy dx equal to a function is a simple differential equation. In other words, I'm trying to find what y is so that the derivative of y gives me the known function f. In order to find y, I have to undo the derivative that's been applied to it, which means I have to integrate both sides. The solutions will be the antiderivatives of the function on the right-hand side. If capital letter F is one antiderivative of lowercase f, then any of the antiderivatives for lowercase f will also work to be a solution of that differential equation. On occasion, particularly when we're talking about motion with position, velocity, and acceleration, we want to know what a particular solution is, meaning that it passes through a particular point on the graph. Let's take a look back at our functions that represented the class of antiderivative functions at the beginning. Let's suppose that I was trying to solve a differential equation and I found that g of x was an antiderivative function for the function that I had. However, the point that I needed to be on the graph was this point here. then g of x, the one in black, would not actually be the antiderivative function I'm looking for. In this case, the one I want that has the particular point on it I'm looking for is g of x plus c3. In other words, there's some point x sub 0, y sub 0 that I want to be on the antiderivative function. In this case, the subscripts 0 represent what's called an initial value. An initial value got its name because in most situations where this was originally applied, these were position, velocity, and time graphs looking at acceleration, velocity, and position, and time was related, so that the initial value was what you got when time was 0. Hence, initial meaning when time began at 0, and hence the subscript of 0. Now we can apply initial value problems in many different situations where the x may not be related to time, but we still call them initial values. Let's go back to the problem below. These words in here give us the relationship between the function that is given and the function that we want. The function we're trying to find is y. We're trying to find what y is equal to, and we're told that the point x naught, y naught is on y as a function of x. The point x naught, y naught is called the initial value. The problem of solving it, where the derivative of y is equal to lowercase letter f of x, and the initial condition is y of x naught equals y naught, is called an initial value problem. Let's solve an initial value problem. This is problem number 500 from the textbook. It tells us that the derivative of f is square root of x plus x squared, and that our initial condition is f of 0 is equal to 2. They want us to find what f of x is. F of x represents our y. Let's find some antiderivative to that original given function and then use the initial condition to find the constant. We will take the integral of f prime of x with respect to x. We'll substitute in its expression square root of x plus x squared in place of the integrand. In the next line, I'm going to split the two terms into two integrals and rewrite the square root as x to the 1/2 power. Remember that each integral symbol gets its own differential. Now I find the antiderivative of each integrand separately using the power rule. The integrand for x to the 1/2, applying the power rule, will give me x to the 1/2 plus 2/2, which gives me 3/2. Dividing by 3/2 is the same as multiplying by the reciprocal, which is 2/3. This gives me a 2/3 at the front. The second one, to apply the power rule for integrands, I increase the power 2 to 3, and I divide by the new power, which is 3. Then I add on the constant. This gives me my candidate for lowercase f. In this case, they did not use lowercase f for the integrand, but instead wrote the integrand as lowercase f prime of x. In other words, they're replacing the capital F of x with lowercase f of x and f of x with its derivative. We want to now use the initial condition, that is f of 0 equals 2, to figure out exactly what the constant must be. To do that, let's first go ahead and clean up our function f of x a little bit. I can do a little bit more algebraically to rewrite it as 2/3 x to the 3/2 plus 1/3 x cubed plus a constant. Now I'm going to plug in the initial condition. My initial condition is that f of 0 equals 2. If f of 0 equals 2, it means then when I plug in 0, I should get 2 for the answer. Using that initial condition, I get 2, which should be f of 0 equal to 2/3 times 0 to the 3/2 power plus 1/3 times 0 cubed plus a constant. 0 to any power is 0 other than the 0th power, and 0 times a constant is still 0, so that I end up with simply the constant, which tells me that my constant here must be 2. That means that my final function, f of x, that meets that initial value is 2/3 x to the 3/2 power plus 1/3 x cubed plus 2. This is the exact antiderivative function that meets the initial condition. Let's take a look at one more. In the final example, we have that the function cosine of x plus secant squared of x is the derivative of some unknown function f. Again, we want to find the function f of x such that its derivative gives us cosine x plus secant squared of x, and that meets this initial condition now outlined in the red box. To do that, we need to integrate. F of x must be equal to the indefinite integral of f prime of x with respect to x. Replacing f prime of x with its expression cosine of x plus secant squared of x, closed with the differential dx, lets us now write two integrals of the cosine of x dx plus the integral of the secant squared of x with respect to x. Notice there is a slight extra bit of space between the integrand and the dx. Now we will find the antiderivative function for those two integrands. What function would you take the derivative of to get cosine? Well, that would be sine. So the antiderivative of cosine of x is sine x. What function would you take the derivative of to get secant squared? That's tangent. So the next one is tangent squared, oops, not squared, tangent of x. Don't forget the plus c. This is our candidate antiderivative class of functions, sine x plus tangent of x plus an unknown constant. Now we need to use the initial value condition. F of pi over 4 is 2 plus the square root of 2 divided by 2. Our initial condition can be written down here so that we'll have it when we're ready to evaluate it. Now we want to plug pi over 4 in place of the variable x in our antiderivative function so that we can pin down the precise value of the constant c. This will give us that f of pi over 4, oops, I don't know why I wrote pi again. Pi over 4 is equal to the sine of pi divided by 4 plus the tangent of pi divided by 4 plus a constant, and it should be equal to 2 plus the square root of 2 over 2. You'll have to remember your trig in order to remember that pi over 4 is equivalent to 45 degrees. The sine of pi over 4 is going to be the square root of 2 divided by 2. The tangent of pi over 4 is 1, and now we need to add plus a constant. What value should the constant be so that this is equal to 2 plus the square root of 2 over 2? I can subtract the square root of 2 over 2 from both sides of the equation, which will eliminate it from both the left and the right. Similarly, I can subtract the minus 1 from the left and the right, And finally, this will give me the relationship between c and the constant I need to get that particular initial value. The constant I need is 1. Now we will rewrite the function with that as the constant. Our function was sine x plus tangent of x, and we'll replace the constant with 1. Our function should be sine of x plus tangent of x plus 1. This concludes this video on how to find antiderivatives based on section 4.10 from the OpenStax Calculus book, Volume 1.